It's my pleasure to do the introductions, which I didn't print ahead of time, so I have them here. So we're very fortunate to have David Mimno here. He's a PhD student at the University of Massachusetts in Amherst. He works with Andrew McCallum along with Andrew's army of people. So before graduate school, he was the head programmer at Perseus, okay, at Tufts University. His work centers around machine learning for text analysis with applications in digital libraries. The goal is to increase the use of computational methods by users of large text collections. In recent years, he's really kind of taken the lead role on MALLET. And for those of you who have been using MALLET for years, you've seen it undergo a huge transformation into what I would say was a prototype research library into a production scale and widely used library for doing all sorts of really cool machine learning stuff. I have been trying to push people around here to use MALLET more, and a lot of people responded favorably, so I thought it would be great to have David down here tell us a lot more about it and give an in-depth tutorial. So, yes.
I would just like to mention that we are recording today's session on videotape. Thank you.
So without further ado, David.
Great.
A great way to quash questions.
Thank you for the introduction. And I just want to point out that if, as Mark has generously asserted, MALLET has become a kind of a production level, stable machine learning toolkit, it's not just because of the people at UMass, it's because of you guys and the MALLET user community. And particularly some of you in this room who I'm hoping to work more with to make it even better. So my wife sent me an email last night that is something basically like, have you seen a weather report? So I'm flying out late tonight, so I think I'll miss all of it, but we've been getting strangely little snow in Amherst. We can see the grass. It's crazy, and I think I found where our snow went. So enjoy. So this is the rough outline. We're going to talk about MALLET. Mostly we could start with representations of data, which leads to a lot of questions. So it's important to spend some time on it. And then three main application areas of MALLET. So we're going to start talking a little bit about the main developer for MALLET is, of course, Andrew McCallum, my advisor. He did most of the work to kind of get it off the ground. But there's been a lot of work by other graduate students in his group and by people outside, especially people at Penn, Fernando Pereira. Mark himself has been a great contributor. What's my role? I'm currently the chief maintainer of MALLET, which sounds really glorious, but it basically means that if no one wants to answer a question on MALLET dev, I kind of take it. And I'm also the chief author of the topic modeling package. That's kind of my focus, which is why I've sort of modestly put it at the very end where we won't really have time to talk about it. The motivation for MALLET is coming out of Andrew's work in text classification and information extraction from the heyday of the tech boom in the late 90s, early 2000s. And the focus is really on text data. And it's important to, when you look at a software package, it's important to understand why was this originally created, because it makes clear a lot of the assumptions that underlie this data. And kind of in an abstract sense, the key assumption in MALLET is that you're starting with text data. And so you never get like 0.75 of a word. You're usually dealing with discrete counts. So even in cases where the methods, and here's sort of a very simple example, even when things have the capability to be continuous and real value, they usually aren't. So that's just something to keep in mind. How do people use MALLET? Well, there's two main ways. Most of the things that you would ever need to do can be done very simply from a simple command line interface. I think this is an audience where I can use simple and command line interface in the same sentence, and nobody laughs at me. Yeah, you're laughing with me, right? And the text user interfaces are usually defined in what we call 2E classes. There's usually a sub-package within a package that defines interfaces. And there's a very nice command option class that handles that. But most of this talk, I hope this is a good direction, is going to talk about the Java API. So I'm going to assume that you know a bit about Java programming. It's also good to talk a little bit about the history of Mallet. There are two main versions. You can sort of divide the epochs of Mallet development into the earlier version and the current version, which we call 2.0 kind of arbitrarily. The biggest change, the most obvious change, is that we went from this very long package name that included UMass as sort of the center to something much shorter, cc.mallet. CC is some island near Indonesia. We're going to create the Mallet castle there. So. And there are also major changes to the finite state transducer package and some other, a lot of under the hood changes, which shouldn't really affect users very much. So if you want to learn more, the first place to start is the Mallet developer website. And we've arranged the documentation there into sort of quick start guides, which focus on command line tools, and developers guides, which are more focused on examples of Java code. And that's, I mean, everyone wants to have more documentation. We're trying to build that up. And if anyone would like to contribute any documentation, that would be wonderful. The other main source is the Mallet dev mailing list. You subscribe by sending subscribe Mallet dev to majordomo@cs.umass.edu. And that's a really great resource, much better than writing to individual Mallet developers, because you increase the probability that someone will know what you're talking about. So one of the big advantages of Mallet is that it's a fairly integrated toolkit that thinks a lot about representations and how people deal with data and convert it into different forms that are applicable for the particular task that you're looking at. Because we're dealing with text data and count data, usually we make a broad distinction in terms of applications between generative models and discriminative models. So are people comfortable with that terminology? Okay, there's just some examples. So this is kind of what we're going for in terms of representing data. So usually when you get data off the web, you're usually not dealing with kind of mathematically trackable things. You're dealing with big document strings, like this one. And what we need to do is convert them into something that we can put into a generalized algorithm that doesn't necessarily know that this is a document. And people are comfortable with vector notation and feature vectors and the semantics of the rows of that. Is that a safe assumption? No, okay. Yeah. So a typical path from the big string that we pull off disk to the mathematically tractable vector representation is, well, we start with the document. What's the first thing we usually do? We get a big long string. Yeah, so we chop it up into little bits, and we get a whole bunch of little strings. So we're still not there. We might do some pre-processing on tokens. The next big thing is we switch from the string representation into integer features. And here we have to keep the semantics of what those features mean in a separate block there. Then finally, we often take that big long sequence of features and squash it into a vector. And here, the values happen to be 1, but there was repeated words. We changed the number rather than the sequence. All right, so how does that get translated into Mallet? Well, everything starts with the instance class. And an instance has 4 canonical fields. There's the name. This usually isn't part of the algorithm, but it's just something for you to hang on to what these instances mean. Distinguishes one instance from another. The data is the primary object of consideration. This is the input to whatever algorithm you have. Almost all of the other fields can be null, and given point, but the data is almost always something meaningful. Target or label, if you have a supervised method, then you have an input and you want to predict some kind of output. So the output goes in the target field. And finally, the source is often empty. It's if you want to keep a representation of what the document, or what the instance originally looked like. That's a good place to put it. Now, there could be many other things that you want to say about a document, and there's a property list inside there that you can put it in, but these are the kind of the 4 canonical fields. And data is really the critical one. So what kind of objects usually go in the data field? Well, obviously first, you probably want to get a string in there, just to start with. Probably don't want to end up with that. But we can sort of model that sequence of transformations that I talked about earlier in terms of transforming the data object from one type of object to another. And so here's that same process in terms of Java code. We start with a string, and we create a token sequence, and that is an array list of these token objects. You can think of right now a token as just a wrapper for a string. We'll talk about it more. There's more to it. And then a feature sequence is basically an array of integers that have some semantic meaning that comes from, well, we'll get to that later. And finally, a feature vector, which is essentially a map from ints to doubles. And the internal representation is more complicated than that because we want to be able to represent sparsity and iterate over non-zero values very, very easily. But you can basically think of it as a int double hash map. All right. So what's the part that I was missing there? It's the concept of an alphabet. So what does a feature index mean? And the internal representation for an alphabet is first of all this T object int hash map. And this is something we get from the GNU Trove library. It's a collection of maps using Java primitives rather than boxing them in objects. So it's a little more efficient. That's the main external dependency that Mallet has. And so that maps an object to an integer. And then the other way, we keep an array list of objects. And so that's how we can look up a particular index and get back the object. That's all internal. How do you use this? Well, there's these two main interfaces. You can look up an object and get an index, and you can look up an index and, okay. You can ask for the index for an object, and you can ask for the object for an index. And as I think you just saw, I have a really hard time remembering which of these is which. If I was doing this again, I'd probably just call it get and assume that but a good way to remember is it, do I have an index and I'm looking up the object for it, or am I looking up the index and getting? Is just remember this, look up index 4. So what's that Boolean out there? Yeah, Dylan?
So the object in hash map dependence is pre-generic days. So is it because it was introduced before generics were introduced in Java?
It was. I don't think it would make any difference because we don't specify. I mean, it is an object, and there's many different things that could go in there, and I don't think there's any. There's no real abstraction that we could get there. I was told to expect a lot of questions from this audience, so I don't know if this is all just too simple, but you know, toss them out there. Does that answer your question, or?
No, I'm just curious now why the difference was that.
Yeah, so we'll get to a place where it is subclassed and there is a so that Boolean is, you might not, usually when the default behavior is if you ask for the index for an object, if that object is not in the alphabet, you will add it. Can anyone think of an instance where or a case where you wouldn't want to do that?
Well, pastime.
Right. So that you might get out of vocabulary words. You don't have a weight for that. You don't want to do anything with it. So there is an option to not add things, and you can actually override the setting of that parameter by using this growth feature. The default is growth is allowed. And actually, if you don't include that boolean, it will by default add something if it's not present.
Unless you stop growth, which uniformly turns off interning.
Yes. Oh, interning is.
Well, I mean, I'm viewing this as intern. The editing is
yes,
intern.
yeah. There was a big long thread about string.intern, and that's a conversation for another day. I have opinions, but. So how do you create instances? Well, there's two main ways. You can directly use the constructor, and in this case, it takes 4 object parameters, which should be familiar. The second is to use an iterator of generic type instance. And there's several, if you look in the CC_MALLET pipe iterator package, so that the package of the classes that we're talking about will always be down here on the left. You can look through that. There's a whole bunch of different instance iterator classes. The ones that tend to get used most often are the file iterator and the CSV iterator. The file iterator is for the case where your instances live each in its own file. And so you pass in an array of files, or an array of directories to start in. The entire contents of the file will get sucked into the data field as a string, and the target field will be some kind of transformation of the directory name. Now that can get you into a little trouble because we don't support Windows paths very well right now. That's something that's kind of an embarrassing failure, but none of us use Windows, so it doesn't bother us enough to fix. And also, if you have testing data and training data in different directory structures, the semantics of how you apply that transformation can get a little complicated. So
you said each file is just gets you one instance?
Yes.
So if you have something like a shard that is a whole bunch of what you want to treat as instances, okay, very good.
A plant. Can you swear that you are not under my? So what I tend to use is the case where you have one instance per line, and there's other cases that we'll talk about later. And in this case, CSV iterator is not a good name. It should actually be called something more like a line regular expression iterator. The basic idea is that you specify a regular expression that has up to 3 capturing groups, which are the things in parentheses. And this is just one way of doing a tab delimited format, but there's many others. And you can also specify where to put each column. So if I had the data in the first column and the label in the last column, then I could specify a number. You can also specify 0 to say this particular field doesn't exist in the file. So if you don't have a label, if you have unlabeled data, then you might not want to use a label for that. Any questions on that? Yes.
So would it be just easier to specify the separator?
Could be. Yeah. If you want to provide that, then that's great. It might be it might create a new regular. So how do we go from one type of data to another? The method that we use is called pipes. And so each of these classes here is a subclass of the pipe abstract class. And again, you see this is actually the same set of transformations that I described earlier. We start by assuming that the data field is a string. The first pipe, the char sequence to token sequence, and remember, char sequence is I think it's an interface that string implements, so you can think of this as a string. It tokenizes, uses a regular expression to define what a token is. The next pipe looks at each token in turn and downcases it. The next one actually changes the token sequence and removes certain tokens. The next to last one takes a token sequence and changes it into a feature sequence. So this one is actually taking the data field out, doing some processing on it, and then setting the data field of the instance to a new class. And note that last one is where the alphabet is created. So when you put the first instance through this pipe, the alphabet will not exist until you get to that point. Up to that point, we're just dealing with strings. And finally, we squash the feature sequence down to a feature vector.
Can you pass control signals through these pipes?
I'm not
In
sure.
other words, just some arbitrary marker that says, oh, I observed some event that's not directly related to the token sequences here, but maybe later on in the pipeline I would want to see that. Or these are just...
It's pretty much just you have an instance and you send it through the pipe object and it does something to it.
But I think for what you're talking about, I stick like, I'll stick things in properties. So like an extra piece of information about the example that I'm going to use later. You can just stick it as a property.
Yeah.
That's
So the way the pipe works is it just implements the pipe method, which takes an instance. And so you can look at anything in the instance. You can look at arbitrary properties. You can change any part of it. All of these pipes have been altering the data field. But some pipes alter the target field. This is probably the most important. This one, if you noticed earlier, I said that the target field is being initially set to a string. What this pipe does is it looks up that string in something called a label alphabet. Now, label alphabet, what's getting at it, is an alphabet that specifically returns or labels. It maps label objects to integers. So what's a label? Well, it implements an interface called labeling, and that requires two methods. There's the get best index. Well, actually several more, but these are the important ones. So that would get the integer code of the label, or it can get the actual label object. And you can also get the other subclass of labeling is a label vector, which would be something that would be returned from a classifier where you don't have a specific label, you just have several labels with different weights. And you can get, the interface for that is get label at rank or get index at rank. So you can iterate through the ranked order of labels.
I'm sorry.
Yep.
Why do you call it best?
So this is if the labeling is actually a label, it will just return itself.
Okay, so when you have supervised data,
Yes.
okay, it's just a label.
Right. If you have if this labeling object is the result of a classification, then it has some uncertainty over which label it is, which is a function of the classifier. And it has it's mapping the label to a weight. And then you can return, so this is basically just, what do I think this is? And sometimes that's a deterministic function if it's labeled.
Oh, I was just saying for the record, this is really confusing. I mean, like, every time I use this, I actually go look up the Java docs again because I don't know what rank and index, like, I never remember what rank and index mean if they're different things, and usually when you return a single label, it doesn't matter, so it's very, very confusing. That's all. No question.
Okay.
Is there an assumption that there's just one label per instance? Or not?
So the labeling interface abstracts away the question of whether there's just one label or a vector of labels. If you're thinking of the case where you have like multiple annotators,
Like the Reuters text classification, a document can be tagged with, this is about coffee, this is about, weather, it could be multiple topics.
Yeah.
Do that all at once.
Mark, do you have a?
I don't know of any class amount that supports multi-label.
Yeah, I mean, my first impression, and I was thinking about this a few days ago, is you would probably just insert the instance more than once. It really depends on what the classifier is going to do with it.
Or use threshold it.
Yeah.
So the question is that can you define your own type of mapping from labels to index to integers? So in that case, like if you have 4 type of labels, so it's like you can map them.
Do you mean if they have a particular order in them, like an ordinal regression, or because this is basically just it's the same with a data alphabet. The index doesn't really matter. It's just we need to represent things as integers in order to put them in arrays. So there's no real semantics for the indexes.
Right. You can write your own, like if you want to build a classifier that has some different sort of labeling, like a sequence, then you just implement a new labeling class, and then you can do whatever you want.
It's so great to have a ringer in the audience.
Oh yeah.
You know what?
Well, I'm telling you what things I don't
Yeah.
like too, so balance it out.
And so in the end, you usually don't want to look at just very few machine learning methods look at one instance. We actually, Eric Learned and Miller at UMass has a paper about classification or machine learning from one instance, but that's the only one that I know. Usually you want more than one instance, and when you have more than one instance, these live in an instance list. And the way to create an instance list is, the syntax is right here. I'm first creating an empty instance list, and I'm specifying a pipe that will tell the instance list how to pre-process data that should live in this instance list. And importantly, the instance list also knows about, it has a link to its pipe, and the pipe records the data alphabet and the label alphabet, if there is one. So that's important to know how to get access to those alphabets. So let's put it all together. At the top, I'm declaring an ordered set of pipes. So there's an array list of generic type pipe. I'm adding four pipes that will do particular transformations. What am I expecting the data to be when I start? String. Yeah. And what will it be when I finish? Right. Okay. And the way to wrap all of that together is to add that pipe list to what's called a serial pipes object. Now that's also a pipe. It implements the pipe class, but it contains a sequence, an ordered sequence of pipes. And finally, I'm going to add an iterator through the pipe for that instance list. Any questions? So in terms of persistent storage, we typically use Java serialization, which looks something like this in code. I was just talking to Mark about protocol buffers. And it sounds like we might be adding that to the standard mallet package, but yeah, there's other things in the works. All right, so now it's your turn. What were those 4 main fields?
Name, data, target, source.
Awesome. Okay. And how do you? What are 2 ways to generate instances?
Constructor.
And iterators. Okay, good. And how what class modifies the value of those fields?
Pipes.
Pipes. Yeah. And just call out some classes that occur in the data field, typically.
Token.
Token sequence.
String.
String. Starts with F. Feature vector and feature sequence. Okay, so the one that we haven't talked about is feature vector sequence, but we'll get to that later. Okay, so now we've spent about half our time just talking about what data looks like. So let's look at what we can do with data, what data can do for us. All right, think most people in this room are pretty familiar with classification. So you get some input, you want to decide which of a finite set of labels is best. Various ways to do that. In code, this looks like is I have a classifier object, or something that implements the classifier interface. I might be a little fast and loose about which is an interface and which is an abstract class, but you can look up in the code and check up on me. And classifier has this one important method, which is classify. It takes an instance and returns one of those labelings. In this case, it's probably going to be under the hood a label vector, unless you have a perfect classifier, or a classifier that thinks it's perfect. And then you can go through and get the best label.
When you say it's a label vector, does that mean that it's a k-best list of labelings?
I would guess it's probably all possible labels with some weight. I don't know of any classifier that returns a k-best list.
What did you say was a label vector? Can you explain?
It's probably a vector of length, the number of possible labels. And each label will have an index that says what label it is, and also a weight associated with it.
What if every label is a tagging of a long sentence, and so there's exponentially many possible labels?
That's the next section.
Thank you.
So this is still the case of classification. Okay, so what are the last two lines doing? So it's just printing out the label and the instance, or the instance and its label. Okay, where do classifiers come from? We have an abstract class called classifier trainer, and that has one method, train. There's many subclasses of that, each for a particular method of training a particular machine learning object. So we have several. If you look in the CC mallet classify package, there are several ways of training maxent classifiers or logistic regression classifiers. But they all implement this train method. Yep.
So there is a top base class for classifier, and then you can write your own classifier too?
Yes. So, but there's a lot more stuff that is involved with training classifiers, right? You don't just do something really simple. So where does that complexity go? Usually you have some kind of function. If you take the log of it, it's a big sum. Often you have to do numerical optimization. So where does that happen? Well, when we're talking about numerical optimization, and just I don't think this will be not a review for anyone, but what we're really talking about is you have some function which takes labels, data, and parameters and returns a value, or it returns a probability. And we want to maximize that probability. We can't change the labels, we can't change the data, so we're maximizing with respect to the parameters. What are the parameters? Well, there's some set of features, and we usually have one weight for every combination of feature and class. Possibly -1, but that's an issue. So in order to train a classifier, and there's some classifiers obviously where we don't need to do numerical optimization, we can just count like name phase or but for something like logistic regression, we need to numerically optimize, and the way to do that is with the optimizer class. An optimizer is a generic method for optimizing a function of some set of parameters. An example would be conjugate gradient, or line search, or limited memory BFGS. But these are all generic methods. So the complexity and the choice for what you're going to do if you implement machine learning methods is going to be in this optimizable class. And the optimizable interface has several sub-interfaces which define what sort of optimizers will take these optimizable interfaces. And some examples are by value, and that would be something like a line search, or more commonly by value gradient. And this is where you have a specific objective function that you can take the value of that function and the first derivative of that function with respect to all the parameters. So let's look at an example. This is the maxent optimizable by label likelihood. This is the kind of long, glorious class name that I absolutely love. I can't stand succinctness in programming. There's certain things that it just has to implement just to be able to pass parameters around. But the two important methods that it has to implement in order to be a by value gradient optimizable are this get value method and the get value gradient method, which passes in a buffer of the length, the number of parameters that is going to fill in with the gradient, or the parameters. So does that get value method look a little funny to you? What something missing there? So the optimizable has to know about its data. You have to give it data beforehand. It's not an arbitrary function of the data. But the optimizer does not know anything about the data. So you can have one optimizer that you pass many optimizables to, but you need one optimizable for every data set. Does that make sense? Any questions about this? No? Okay.
Sorry, quick question.
Yes.
Suppose you want to tamper with a stopping criterion or something like that. In that case, you would subclass the optimizer?
Yes, I think that's correct. I don't think...
You can't run it one iteration at a time or something like that?
You can...
I think you can.
Yes, I think you can run optimize with a number of iterations,
I see.
if that makes sense for the optimizer.
And then if you run it more iterations, it picks up where it left off, or it restarts?
Yes, it picks up where it left off. Yes, I believe that's true. I might want to check.
Thanks.
If you want to do some more complicated stopping criterion, like don't stop until you haven't changed the parameters in 3 iterations instead of 1 iteration, then you would have to subclass the or write a new optimizer.
Why couldn't you just say run one iteration, check, run another iteration, check, and do it outside?
You could do it that way.
Yeah.
So for your LBFGS optimizer,
Yep.
so you have all sort of like line search methods for finding the subfunctions?
Yes. So there's a separate optimizer for line search that is called from within the LBFGS optimizer. So often you want to know how good your classifier is. Typically the way we do that is cross-validation. MALLET provides some great methods for easily doing test and training splits. In this case, the instance list class contains a method that will take a random number generator, and this is our own special random number generator randoms class. The extra S is to distinguish from the Java util random class. So we can import java.util.star, which we're lazy we like to do, and also a vector of proportions, and that should sum to 1. And so this is saying, what this does internally is shuffles the instance list and then takes the first 0.9%, puts it in a new instance list, takes the next 10%, puts it in a new instance list, and takes 0% and adds it to an empty instance list. There's also a cross-validation iterator, which will create multiple cross-validation sets. And it does do that randomly. It doesn't try to avoid intersections between the test sets, just something to know. So finally, you can evaluate classifiers by creating a trial object. Now, this is basically a wrapper for a classifier and an instance list. And it has this interface of different methods that or different statistics that you might like to report about your classifier. And it's basically passing those on to whatever the classifier object is. So your classifier should implement these under the hood. All right, it's that time again. So I've just invented David regression. What's the first class that I should implement? Yeah, so I need a classifier that just does my classification. How should I train it? Right. So classifier trainer. It happens to be this kind of classifier that I have a log likelihood and a derivative of that. What do I need to code for that?
Optimizer?
Optimize subbolt. And what sub interface is that? Yeah, Python. Okay, I was asking that question. Okay, and how would I check whether my classifier is better than my interface?
Trial.
Yeah. How many trials?
We need trial 3.
Yeah. And so what specifically, how am I going to create my trials? So I'll create one trial with
one of the classifiers in the same instance, different classifier.
Yes. So the two arguments are the classifier and the instance list. So both classifiers I'll pass the same instance list, but I'll give them different classifiers. Okay. So yeah.
Right. There are two questions, and they're two in depth, just you can skip them. The first one is classifier factories. So those showed up, and I haven't quite figured out why. So what's the idea behind classifier factories?
Fine.
Okay. Number two, is it because you don't know or you don't want to answer?
Both.
Okay, good. Just checking. The other one is doing parameter time. So what happens under the hood in these models is it does the cross product between your alphabet and your label alphabet to produce parameters.
Yes.
So you don't have to handle any of that.
Exactly.
But it means that there's no obvious way to do parameter time across labels. So, either the ways I do it, the question is there a good way to do it without, breaking too much open and just fiddling yourself?
I think you'd probably have to go into the optimizable
Okay.
and just change the value gradient.
Okay.
Does that answer your question?
Yeah, I mean, that's basically what I do, but
Yeah, I don't think there's any.
like for hierarchical classification, there's some easy things to do with parameter tying, and it seems like you basically need to re-implement things rather than.
Yeah, I don't see a good way to do that abstractly without making everything else more complicated. So.
I agree.
Yeah.
That's why I asked, because I don't know how to do it.
So sequence tagging, are people familiar with that?
Sorry, I had a question. So you told us how to find out whether the David classifier beat 90 Bayes. How do we find out if that's statistically significant? Is that built in?
R. Yeah, we don't have good. I was telling people I just got this book out of the library, 100 statistical tests. So I think Mallet will start getting better at frequentist testing. But there's a lot of ways that I think we should.
Well, the basic thing to put in, I think, would be a paired permutation test.
Yeah.
And there's a guy named Axel Gandy who has worked out procedure for figuring out how many samples you need to do.
Okay.
How many bootstrap samples you need to do. I mean, it's one of these things where the stopping time is a random variable.
Right.
And you have to be careful.
That doesn't.
Yeah.
Yeah. No, that's a great question. And that's something that's been on
I have a question. So you might have an answer, but so what if your data is not string and you want to start with features? You could do it easily without.
Yeah, and actually we'll go through some of that right now. So sequence tagging, we're going to use the example part of speech tagging. Everyone I'm expecting is familiar with that. And obviously we want to predict what the sequence is for an unknown sequence. As Jason was helpfully pointing out, there are an exponential number of possible sequences of labels. Is this what you were referring to? Okay.
Structure prediction.
Yeah. So the thing that gets us out of this problem is one of the things is the Markov property, which is due to Andrei Markov. Oh wait, sorry. No, this Andrei Markov. It turns out that Michael Jordan is not the only statistician who has to compete with a sports figure in search engine.
Well, Markov is actually quite a common name.
Yeah. So it's basically that there's a certain finite history that you have to go back in the sequence before it doesn't matter anymore. So if you're trying to get the probability of being in a particular state at a particular time, then you start being able to forget certain things. So David Smith, who's now at UMass, I think his exact words were, people at Hopkins eat dynamic programming for breakfast. So I'm hoping that you all are fairly familiar with this.
Jason,
The rest of us just use Dynamo.
Yeah. So there's several different ways of doing sequence tagging, and they're actually under the hood almost exactly the same. And it's just a question of how they're trained. A hidden Markov model is a fully generative model, so that means that if I start from nothing, I have rules with which I can create a sequence of both hidden and observed variables. But that means I need to have a very good estimate of the density of the full joint distribution of data and labels. And that implies that I need fairly strong dependence assumptions if I want to do even a remotely good job. Conditional random fields is a very similar model, but the objective function is the conditional probability of the labels given the data. I'm not trying to estimate the density of the combinations of observed features at all. So I can do, like, rather than just have the observable value be a single string or a single feature, I can have multiple features of a particular observation. Are any of these features not independent? Yeah, pretty much all of them. And if I was trying to estimate the density of the co-occurrence of these features, then that would be a nightmare. Just representing that distribution would be awful. So what does that mean in terms of MALLET code? Well, the input for a hidden Markov model is a feature sequence. And that's, just, as I said before, it's essentially an array of integers. So I only have, MALLET is currently structured so that you only put one feature on each observable point in the sequence. Whereas the input for a conditional random field is allowed to be a feature vector sequence. And so this is an array of feature vectors, which is a sparse representation of features to values.
So I ran into this a couple years ago. Why do you do this? Because there's no reason you can't have them both be feature vectors. I mean,
Yeah.
You had a very nice story, but like you can have lots of observations at the same point.
Yep.
So
Maybe we should change it.
okay, great.
Yeah. So, for example, one great thing that MALLET does is read what we call the simple tagger format. There are probably other names for it, but essentially you have a text file that has one token or sequence element per line. The last element of that line is the tag, and everything before that is a feature. So in this case, we only have one feature, which is the exact string. But we could also do something like this, where somehow, maybe with a Perl script, maybe with something else, we have generated a whole bunch of features for each position in the string, or in the sequence. So this is a really flexible way to do complicated things with data. But we might want to do that in MALLET. So here's the way that we would handle the first case, or the second case where we already have our features. start with the line group iterator. This is another of these iterators of instances. It reads through a file and creates a token out of each line. Getting ahead of myself, forget that. It just reads through the file and breaks it into strings every time it sees a blank line. And you can actually specify the regular expression that means end of an instance. This piped simple Tiger sentence to token sequence, that breaks the lines up into tokens and creates token objects. You'll notice that the token now has arbitrary numbers of properties. And in fact, there's no distinction between the feature me and the feature 2 letters. It doesn't know the difference. It doesn't privilege any particular. And finally, we can change, again, the token sequence to a feature vector sequence, which is going to look at all the possible properties.
You're saying even the label isn't different?
The label is the one that's, so it only,
okay.
It splits off the last element.
Can you say, if you happen to have a file where it's not the last, so you say it's here?
No.
You can't.
But if you want to, you can write that pipe. Probably wouldn't be very hard. But we might want to stick things in here. So let's talk about those right now. And these are all going to live in the Mallet pipe TSF package. That stands for token sequence features. It happens to be the finite state transducer backwards. But that doesn't mean anything. I was trying to figure out like why, but no, it's just random. So here's some examples of pipes that take token sequences and return different token sequences. The first one is going to take a suffix. There's also a token text char prefix pipe. And this is going to take, so at the top we start with just the feature Ishmael. After that first pipe, we've got this additional feature C2 equals EL. So what's done is take that string C2 equals and added the 2-character suffix. In the second one, we're specifying a single feature cap. So notice that the previous one could specify arbitrary numbers of possible features. I guess the limit is the number of pairs of Unicode characters. In the second one, we're specifying a single feature that is either on or off, and it's going to be whether we match a particular regular expression. And if you know anything about the Java regular expression package, this is calling the matches function, which only returns true if the entire sequence matches the regular expression. So you notice I put in that dot star. If I didn't have that, then this would not match. And the dash P is uppercase Unicode characters.
That's matching the entire previous line, including the feature on the end? Or just Ishmael?
No, that's a good question. I believe it is only matching the first one.
But you are in general allowed to have things that look at the previous computed features?
Yes, we'll cover that in just a minute.
And so I think regex matches is looking at the token value specifically,
Okay.
and not the features. So it's because the token is Ishmael, but it just looks at that.
So we've also got this lexicon membership where you can have a big list of things. That's pretty clear. Okay. You might also want to have what you might call sliding window features. So if we're adding features for the token dog, you can see my son's like go dog go. So we might look at the previous one. It's red, and so we might add the feature red at position -1, a at -2. We go forward, and we can also have conjunctions of two previous or the previous and the current string. So this is a way to lexicalize the features. Way to do this in Mallet. We would create a multidimensional array of integers. I'm saying I want 3 conjunctions. The first one is just going to be -1. The second one is just going to be +1. And the third one is going to be -2 and -1. And so this will create features like this: A at -2 and red at -1, on at 1. And it will, if you look at the order of things, create features like this one: A at -2 and C1 equals ED at -1. So you do have to consider the order that you're adding these token sequence feature pipes. So finance to introduce transducers. Basically, the point I'm making here is that each one of these transitions is governed by a particular weight or probability. And the question is, how many of these weights do we have? This is an important question. Because the number of parameters and the number of weights that we have to learn and the size of our gradient vector directly affects performance of the trainer, and it also affects overfitting. So one trick to reduce the number of parameters is a simple model will have a weight for every combination of possible sequences that can one that can go to the other. But if you think of most sequence tagging cases, it might be very unlikely or impossible for example, a determiner to be followed by a conjugated verb. Yeah. So this may not be a good idea.
But you should probably observe it, right?
But one way to reduce the so then the question is, which transitions should you not allow? And the approximation that seems to work a lot of the time is just to look at your training data, assume it's big enough that you get a good representative sample, and zero out. Don't even represent any transitions that don't occur in the training data. Another question is, what sort of order Markov assumption do you make? There's various topologies that you can choose. The first one is pretty much the standard hidden Markov model. So you have a weight between every pair of states, every allowed pair of states, and a weight between the current state and any observed features. This next one is a model where it might be more clear if I used a factor graph notation, but how am I doing for time?
It's 2:30.
So here we have a weight between every pair of subsequent states and the feature. So that will have a factor of the number of transitions, more parameters than the previous model. Or we could even go crazy and have something that has weights between all triples of states and all the features. So again, we're multiplying the number of features, which could be very large by this. Let's see how we do this in MALLET. We have these 2 classes. There's more, but these are the important ones. CRF and HMM. And we have trainers, as you might expect. To create this model here, so this is the model where we have a weight for each pair of states and observed features, then we can either we create a new CRF, we tell it what its pipe is, that implicitly gives it access to the label alphabet, the data alphabet as well. We can either add fully connected states, which will add the whole matrix of states, or we can add states for labels connected as in a particular training set. And that's usually the training set itself. To get this model, we would add states for what we call 3/4 labels. I take no responsibility for this terminology, but that's how we describe this model. And this actually often, it's not the default, but it often produces much better performance. This is a second order model, so this is by labels connected as in. And this model is something that we call half labels, or half order. And the reason that this is not 0th order is because we've said we want to zero out certain connections. So it's basically creating a binary probability on, or a uniform probability on which state can come after another state. So it's essentially a max limit model, but certain transitions are not allowed. Any questions? So we can train this transducer.
What is the second argument that is set to null there for creating a serum?
Next slide.
It's here.
No, right there.
So there's an input pipe and an output pipe. I don't actually know what the output pipe is for, and I didn't get around to figuring that out. I was hoping nobody would notice that. Mark, do you know it? The output pipe? Okay. All right, Mark will get back to us.
I didn't think I thought it was something else, but if you say it's an output type, I believe you.
I'm fairly sure, but I'm like.
David, a few quick questions about how far you can take this. So if you want to specify your own topology, presumably you can do that. You don't have to call one of these standard routines.
So you might have to subclass CRF, but it has a method for add state.
Yep.
And you can add connections between states.
Okay. But how about variable length engram models where it's data dependent? How far you look back?
That's a great question.
Another question is structural learning.
Yeah, you probably have to do some kind of trainer for that. I don't think we support that as is.
Okay. And you do know anything about the variable length case?
No.
I mean, what you really, the way I think about these things generally is not in terms of graphical models when it's linear chain. I think about it in terms of finite state machines.
Exactly.
In which case you could split some states more than others and everything just kind of falls out.
Yeah, I know other people have been working on that kind of question, but I don't know what the results are.
Well, I mean, there's not sort of a good toolkit for it. So OpenFST doesn't have training built in. We've extended it locally to do training.
Okay.
But it may not do all the kinds of training that you do. So.
Was it difficult to extend it? Or?
Well, they have an extensible weight class. So you can put in a semi-ring of your choice, and it can keep track of the.
Okay.
It can keep track of things. So we have papers about that going along with that.
I don't know a whole lot about the internals of the CRF class. I would suspect it's pretty solid, and I would guess it wouldn't be that hard to extend it, but I make no.
The problem is it's like having switching variables in a graphical model. I don't know if you support that.
Not that I know.
So it's like data-dependent topology. That's what makes it tricky. And some of the methods that you might want to support for inference might be sort of only for regular graphical models, and if any edge could possibly be there, then it has to be there all the time,
right.
And that slows you down.
Yeah, I don't have a good point.
Thanks.
Was there one?
Yeah. So if I want to implement a script train CRF, can I also do this here, or do I need to download GRM and can only do it in this?
I think you would probably need GRM. So GRIM, I think he called it, is Charles Sutton's extension of MALLET CRFs to arbitrary structures. And he's done things like skip change CRFs. I'm not sure if he is currently actively maintaining, he does answer questions about it. So, anything else? So you can do the same kind of thing. You can create a transducer evaluator and pass that in. And what this will do is every time it assumes that you have an iterative optimizer, and every time it runs an optimization iteration, it will call all of the transducer evaluators. And that string there, the testing, is to remind you which evaluator this is. So you could, for example, pass in your training data to one evaluator and your testing data to another evaluator, and it would give you that. So if you have a trained transducer, you can do something like this. Can someone tell me what this is doing? Okay, so we're creating a sequence that's the output of the transduce method on some instance which is an input. And then we're iterating over the length of that sequence and printing out the input and the output.
And is there, is it possible that output.get of index is multiple symbols instead of just one?
Yeah, so here we're just calling the toString method, whatever that does.
Right.
So I haven't tried this. I don't actually know what it does.
Well, I'm not actually asking about the print. I'm asking about the return type of output.get. Could that be different? I assume that the return type of input.get is a single token.
It will be a label object.
Okay. So this kind of transducer doesn't allow, the input and the output strings have to be the same length. Input and output sequences have to be the same
It
length.
actually has an assert that they are the same length. So internally what this is doing is there are two classes, sum lattice and max lattice. And this is calling max lattice and then getting the highest weighted output. Now the max lattice does implement an A-star search, so it can produce k-best lists. Unlike the standard classifier, which just does the finite number. I think I'll just run through topic modeling.
I have an answer to
Yeah.
the output pipe. I'm
Yeah.
not sure you're going to like it, but you can tell me what it does. So an output pipe takes a sequence that has been labeled, so it's target. So what it does is it assumes that the target is now the labeling that's been applied to that sequence. And then the idea is that the pipe will transform that instance in some way to put a string into source that reflects the labeling.
Interesting. Okay.
Yes.
I have not used that.
No, I don't know why it's in here.
Yeah.
It's very strange.
Somebody must have used it.
So if anyone needs to go, please feel free to. So the idea, going into topic modeling, this is kind of where I'm really on much more sure footing. So I hopefully won't have to delegate to Mark to answer your questions. But if you think of a news article, then you might imagine that it's about some sort of topics or semantic elements. It might be something like sports or negotiation. And you might also be willing to believe that if you think about sports, you might, there's actually games that involve this, that you sort of think of words that are associated with sports and think of words that are associated with negotiation. But in actual data, all we usually get is this, just a bunch of words together. And a topic model is a method for teasing out the distinctions semantically between words based on co-occurrence patterns within documents. So don't say anything, but raise your hand if you know who won the 1994 World Series.
Does no one know?
Okay, so now
Wait, I have an internet.
Yeah.
don't go to the internet. So with that in mind, is there anything? So for example, my model one on New York Times articles for the last 20 years has found this topic. It seems to be, I recognize that these words are semantically together, but if I plot it over time, there's something a little weird happening here. If you look at 95, 94, then I noticed that it also seems to have a correlation with this one. So and this is just an example, but this model has found the players' strike. So the World Series was actually canceled that year.
Oh yeah. Oh, yes, the World Series. Oh, the White Sox group. Okay, yeah, no.
Yeah. It was the Expos' year to win, and they never recovered.
I would say so. It was the White Sox year to win, but they recovered.
Yeah, they do. So just to go over this really quickly, there's this kind of interface in MALLET for training a topic model. You specify a number of topics. This implements a parallel multi-threaded topic trainer, but you don't have to use it. You can just use it with one thread. You specify some training instances, and you say go. So it's not supervised, so it's a lot simpler in terms of adding features. We've recently added some methods, and this is coming out of my own work. It's a KDD paper. No, sorry, this is the ICML paper. You can get the log likelihood of a held out training set.